Okay, I'm going to go through this first, I guess, official machines ILM. The math apps, again, was review from first, second, and third math concepts. So some of this stuff is going to be review as well, too. We did talk about AC generation in second year. So some of the stuff is, again, not brand new information, but they kind of go into a little bit more detail in the next mod even. So this one's kind of general. So we'll get through this one and some general concepts, and then we'll get a little bit more into the specifics of DC machines in the next mod. So this one does talk about AC and DC, especially in the first part of the module. So I don't have it in my PowerPoint here, but basically pages 2 and 3 are going to be terms. Okay, so make sure to go through those machine terminology definitions, because they'll explain to you about the field winding, armature winding, the difference between where they're located, whether we're DC or AC, difference between slip rings, split rings, all that kind of stuff. Okay, so make sure and read through those. I won't read through them here, and I don't usually in my lecture, but they are important, and some of our questions are in our Blackboard. We'll definitely test you on those. So first thing we want to talk about is the actual, I guess, definitions of electromotive force and induction. Again, we did talk about this in second, but we'll review it here. So we just want to make sure that we have an understanding of electromotive force. That is our EMF, that's our voltage. So it's produced by rotating the armature winding conductors within a magnetic field produced by the field windings. Okay, so the field windings have current going through them, creates a magnetic field. Then when we have an armature winding cut through it, that generates a voltage as long as we have a closed loop. Okay, so we'll talk about that. There'll be some pictures here coming up. We just have to have a way to have general motion. So either the field has to move or the armature winding will have to move. Either way, again, it depends on whether we're talking AC or DC on how we do that. Then electromagnetic induction, again, the production of a voltage in a conductor because of the relative motion between the conductor and the magnetic field. So then we have a voltage being induced once we have that motion in between. Okay, but again, this is, make sure you read through those definitions so that you have an understanding of some of the terms that they're going to use throughout this module. So Fleming's left-hand rule, this is basically going to let us know which way the current is flowing, because again, when we talk about it, we're spinning a armature 360 degrees through a field. Current is flipping back and forth from our sine wave. So it's peaking positive, then peaking negative, back to zero. Okay, so we want to know which way the current is flowing. We have to know the direction of the flux, so which way the north to south is. So these magnetic poles would have to be labeled for us, because we're going to put our forefinger pointing from north to south. So this finger here is pointing from north to south. So we have our left hand up in front of us pointing north to south. The thumb is going to point in the motion of the conductor. So in this case, it's pointing up. So then we point our middle finger in the direction of current, and we can see that our middle finger is pointing at us, or basically in this scenario would be coming out at us on this conductor. Okay, so Fleming's left-hand rule is going to be the one that's going to show us how we can do that. But again, we have to have 2 out of the 3 pieces of information in order to find the missing one. Okay, so they'd either have to give you the direction of flux, direction of relative motion, or the direction of current if they wanted you to find out either one of these. Okay, so we did cover that in second as well too. So we're kind of revisiting these concepts here, but again, stuff you definitely, I would imagine, did not do in the field very often. So the magnitude of the EMF, so that's the amount, so how much voltage are we going to get, depends on these 3 things right here. So flux density, so basically the strength of the magnetic field. So if in this picture they kind of just look like magnets, they're not electromagnets, we don't see a wire going across there. This magnetic field strength would have a value, okay, and that we would refer to it in this would be the flux density. How dense is that magnetic field? How strong is it? The effective length of the conductor that's within the field, and then the velocity of the conductor. So how large or how long is the cable, and how fast are we turning it in that field? Okay, like almost like an RPM when it's spinning around. Okay, because if we have a prime mover like on a generator, we have a combustion engine that's spinning the armature windings within the field windings, and that's going to generate a voltage depending on how fast we're spinning it. Faster motion, higher voltage. Okay, more flux density, higher voltage. So this is that kind of this formula right here is going to show us, that these are all directly proportional. So the amount of EMF is going to increase if this increases, E goes up. If the length increases, E goes up. If the velocity increases. So if any of these values increase, we're going to get a higher output voltage. So again, E, the instantaneous induced voltage, so that's the amount, the magnitude that we're going to see there. Then B is the flux density measured in Teslas. The flux density is the easiest way that we're going to be able to alter it. The length is going to be fixed. We're not going to be able to change that. The velocity is something that we're going to maintain. So one of the only things that we're going to be able to change in order to increase the magnitude of voltage, and the easiest thing is going to be the flux density measured in Teslas. Yeah, sorry, to restart here. So yeah, again, the only thing we're going to be able to change easily is the flux density. So just think of it like if they were permanent magnets, like this example here, where we don't see any wires around a piece of metal, that's going to create an electromagnet, which is normally what we would have. In order to increase the flux density would not be easy. Okay, if these were fixed permanent magnets, we wouldn't have the availability to do that. But a electromagnet is a different thing. An electromagnet is basically when you have wires wrapped around a core that creates a magnet depending on the amount of current that goes through. So if we can adjust the current, we can affect the amount of field intensity. More current, higher magnetic intensity. Less current, lower magnetic intensity or flux density. So that's how we can change the amount of magnetic lines of flux in this machine, is by changing basically the current going through the field windings. So the field windings create a magnet is what they do. And we can basically change the intensity of that magnet by changing the amount of current through it. So if we can put a field rheostat or a resistor in series with the field winding, we can affect the amount of current that's going through there. Okay. The next thing they talk about in your module is basically just the generation of this AC sine wave again, where we are running with, if we're running parallel with the magnetic lines of force, so we would think that these magnetic lines of force again are going north to south, so we have all these lines going across here. When we're parallel with them or not cutting them, we're basically not going to be inducing any voltage into that wire, and that would be at our position at 0 degrees. Again, if we were going back to as they do here, coming up here, we'll go tie this onto a sine wave as well too. So at 0, where it's sitting right now, it's not cutting any lines, so it's not generating any force. It's not inducing any EMF. Once we start rotating, we start cutting the lines, okay? And then at 90 is where we get our maximum generation. And we'll revisit that when we come through. The other thing that we want to make a point of here is the difference between slip rings and split rings. Now, when we're talking about AC generation, we use slip rings. So basically, it's a connection point with the brushes here and here for our load. Because this is spinning around, potentially at 60 hertz, okay, we can't have a connection that's solid to that. Otherwise, obviously, these wires would just get all wrapped around each other. So that's why we have slip rings and brushes to minimize the arcing, where it just sits and makes contact. The whole time that's spinning around, it makes contact and then puts a voltage to our load. Okay, so in AC, we're going to use slip rings, and that's because this thing is going to be spinning around, and we want to see that positive peak and that negative peak, okay, and our sine wave. So again, we're at 0 here, 0 degrees, not cutting any lines. As we rotate through here, now we're at the maximum amount of cut at 90 degrees with the field. So now it's perfectly perpendicular. So when it was up here vertical, we were at 0. Now that we're cutting all the lines of force at 90, that's where we're seeing the maximum amount of voltage generated. Then it's going to continue rotating until now, you can see obviously the color, the brown here. It started at the top, so the brown was at the top here at 0. Then it moved down, or moved to 90, generating cutting the most lines of force, generating the highest voltage. Continuing now down to 180. Again, now parallel with the lines of force, but in the opposite position. We were up here, but still parallel, generating 0. Now when we keep coming through, now we're at 270, and we're generating maximum voltage again because we're, again, perpendicular, or cutting right across the lines of force here. And then we continue all the way back up, and we're back to 0. And then the cycle just repeats. Okay, so this is our generation of our AC sine wave, just like we saw in second year, okay, when we first started talking about alternating current. And again, alternating voltage as well too. So these are different values. Current's going one direction in this area, then current's going a different direction in this. So alternating current that goes one direction, then flips around and goes the other direction. So this is how we generate our AC voltage. Okay, our alternating current voltage, we're going to use slip rings, and we're going to basically generate a sine wave. Again, I think of these lines of flux, I go back to this drawing here, I think of these almost like kind of like rubber bands, if you will, going through here. If you have a conductor that's going right beside them, it's not pushing on them at all, so it's not generating any force. As we come across, imagine if these were bands, how much force we would have to push once we got, that's what the force, think of that, that's generating that voltage there. Okay, and then when we come around again, we're parallel, 0, because we're going right alongside of them until we cut hard. Again, right at 90 and 270 to get that maximum voltage generated. Okay, so then they talk about DC, okay, and the split ring instead. So they talk about here controlling our output voltage. Again, the magnitude, flux density is going to be our big thing that we can change. We could change the speed, we could change the number, but again, that's hard to do on the fly. Okay, that's stuff that would be, we want to run it at the frequency of 60 hertz because that's what we run here in North America. And when the machine's built, it has its number of turns and its length of conductor, all that stuff already. Okay, so we can't change that on the fly. So the easiest thing to do, again, is to affect the field. Now, the module shows these as just magnetic poles, but you got to think, in reality, there's wires wrapped around this pole, down through across, and then wrapped around here. I got a drawing I can kind of show you to help bring that concept a little bit closer here after this this lecture. I'll show you. Just to show you the difference between a permanent magnet and a electromagnet, okay? Because that's the big difference. If we have to have an understanding this is an electromagnet, that's why we're able to vary the intensity. Okay, if they were permanent magnets, we would not be able to do that. So again, this relationship still is E is equal to BLV. Okay, those are the things that are going to basically determine how much or the magnitude of voltage we're going to get. So now in a DC generator, and we're going to talk about DC first once we move on to the next module, the biggest difference here is that we have these split rings. And what that's going to do is it's going to basically stop the alternation at 0 and kind of just restart it over again instead of going down into the negative. So again, we're start at 0 degrees, we would see 0 voltage. Then we go to 90 and we can see the current flow at that point. Again, maximum voltage induced at that point. Then when we go back down to 0, okay, that's where the split happens. So it's kind of like a restart, and then it flips back again because of that split ring, and you can see currents going in the same direction, even though the brown is on this side on this alternation, and it's on this side here. Because of that split, the current doesn't change. So we don't have alternating current anymore. We have direct current where it's always going, the current's always going in the same direction. Now, it's not like a battery output that's usually just a straight line of DC. This is called pulsating DC. Okay, still though direct, not alternating because the current is never changing direction, but it's pulsating instead of a steady state value, which is what you would normally see come out of a battery. Okay, so where the split occurs, it basically think of it as restarting the alternation over again. We're never going to carry down into this negative alternation. It's going to flip it back up into the positive. So now we have multiple positive alternations instead of a positive and a negative like we do with AC. So again, the split happens at 0 and basically kind of restarts it over. So just think of it like that. We still get the peak voltage induced at 90 and 270. Again, just the current stays the same direction. So big difference between slip rings, AC, split rings, DC. Okay, you're gonna have to make sure you know that. Multiple loop windings. Again, we've been showing one single loop through there just for relative ease of the diagrams. What they're going to say is if we want to add or have more output, we would just add more loops. Okay, so we're kind of changing the L of the BLV now. So to attain reasonable values of voltage, again, higher value, usable, like our standard 600, 208, 480, 240, whatever the case may be, we have more than one coils with more than one loop. So it says here the 3-loop armature coil below would have 3 times the output voltage of a single. So again, the more loops we have, more output, and we would match the output of what our standard expectation is from a voltage source, be it AC or DC. Okay, so we add multiple loop windings in order to increase the output as well. Now they talk about improving the waveform. So we have this pulsating, again, this pulsating, in this case, DC coming out of here. Okay, and they say progress in the cycle, just for review, a cycle is a 360-degree rotation. An alternation is half a cycle. Okay, so one bump is an alternation. It takes 2 alternations to make up a cycle in AC. In DC, we talk about it a little bit differently, but in AC, we'll just say a full revolution, a 360 degrees is a cycle. And also important too to kind of touch on in that DC generation, even though we have these pulsating DC where we don't have the negative alternation, the armature winding is still spinning 360 degrees. So technically it's still generating AC. It's just it's the split rings that output it as DC. Okay, it's not like we're just going back and forth from 180 to 0, like we're not doing a full revolution. If it's attached to a combustion engine, it's still spinning on a 360-degree circle. Okay, but the output is pulsating DC. Okay, but it's still a full 360-degree revolution. Whether I'm talking AC or DC, it's the split or the slip rings that determines the output. Okay, so this is saying here, how do we improve the waveform? So this pulsating one, it's okay. It's going to give us DC because we're not getting this alternation, but we have these big valleys and peaks where we see a maximum voltage, then we go to 0. Then we see a maximum, then we go to 0. And some pieces of equipment that need DC are okay with seeing that. Some pieces of equipment like electronic devices do not like that. So they'd rather see a steady state of DC. Okay, a nice, almost a straight line would be preferable. Okay, so what they're saying is by increasing the number of coils and commutator bars, the generator will produce a smoother output. So again, it still fluctuates, still has that ripple, but we don't get these super deep valleys and peaks. So by increasing the coils and the commutator bars, it will produce a smoother output. So here's the resultant output. Again, we're almost staying at the peak value higher because we're not going, we're kind of just seeing this bit right here, the tops. When it wants to go down, it's already picking up by another set of windings. That's, again, if this would be, there's 3 of them, you'd split them evenly apart, probably 120 degrees. So while one's just about to drop, it catches the other one and brings it up. Catches the other one, brings it up. So we don't get down into these really deep valleys of 0 volts being generated. So if we can add more coils and kind of put them, have them peak at different times, then we can smooth that output. Okay, and again, we're trying to get as smooth of an output as possible. A straight line would be perfect, but we can only do so much. But this is definitely better than the peaks and valleys that we see with just the one. So when we talked about controlling our voltage output or the magnitude, again, I said it quite a few times here, and we'll talk about it again here with this controlling our output voltage. We can control the intensity. The field intensity is the easiest thing we can do. So again, here's our supply. We're sending DC. This is the field winding. Again, this is wrapped around a piece of metal that's going to create a magnet. That's what this field winding is going to do. Now, if we adjust this rheostat, we can adjust the amount of current going through here. Thus, we adjust the intensity of that magnetic field. Okay, so by changing the amount of current through it, we're going to basically increase them, whether it's a strong magnet or a weak magnet. Okay, and they're basically saying we increase the resistance, reduces the current. Okay, that's some Ohm's law for us. And if we decrease the in field intensity, and it's going to reduce the generated voltage. So if I have a weaker magnetic field, I'm going to basically produce less voltage. If I want to increase the voltage output, I would decrease the field rheostat, which would increase the current going through the winding, which would create a stronger magnetic field. Thus, I would be cutting more lines of force with every rotation and generating more voltage. Okay, so this is why this is the easiest thing for us to adjust, because we could literally adjust this on the fly. So even as the generator's turning, I could adjust this field rheostat on the fly and change the output voltage. Okay, but we can only get so much. Okay, we can't just keep, well, yeah, let's just keep cranking current through there and crank this, create this giant electromagnet that's going to just give us all this free power. Okay, there is still limitations based on conductor, based on the type of core, all that kind of stuff. So when they talk about this relationship here, they're kind of showing that there is a point where we would get into magnetic saturation, okay, where we've basically magnetized the core so as much as it can do, okay, and that's going to hit that knee, and then we're going to hit there. And after saturation, we can still increase it, but it's only going to increase the output voltage by a minimal amount, okay? So that's when we've reached saturation. We can't just again, keep cranking it, continue building voltage from nothing, okay? There's a limitation to this. Now, we have to remember too that even when it's spinning through there, even if we drop this down as low as we can, they're going to just say that it's never actually at zero. We're going to have some voltage generated if this thing is moving, if we have our armature winding moving through the field, even with this very small amount of current going through there, or again, they're saying with it off, is there's going to be enough residual magnetism in the core of that material in the field that we're still going to get a voltage. So even without with our field rheostat cranked the highest as it could go to allow no current through that wire, we're still going to see a very small amount of voltage generated. Okay, and we'll see that when we do our lab as well too. Very rarely can you turn a generator on, have it rotating through a field, and not generate anything like an actual zero. We wouldn't see that. It would still be like 10 volts or something. Okay. Again, so watch a question that says, does it generate zero? No. Close to zero? Yes. Okay, so just watch that little caveat there. So that's the end of the module. They do talk about nameplate information. I haven't really gone through that as much. It's kind of straightforward. Just make sure you're reading it. It does say typical ratings for pieces of equipment. I'm just going to end this here. It does say some important stuff in there, but just read through it the best you can on your own here. I'm going to just open up here what I'm talking about. Okay, so this is objective 3, basically on your output, your rotational frequency. Gives you some common outputs for RPM, some definitions too, but mainly just what we're going to see on nameplate information and what we're going to pull off that's important. Okay, so definitely go through this stuff too. Have a read through it. It'll tell you how to go through and identify everything that's on these nameplates. Okay, again, probably more field applicable than anything. The one last thing I wanted to show was just that kind of that design of the electromagnet, and I think I got it drawn out here so I don't have to redraw it so much. So I would kind of draw this usually up on the board, but so here's kind of a breakdown of what I would see as, just to kind of make sure the difference between we have an understanding between the permanent magnet and a field winding. Okay, if we had a permanent magnet and we rotate the armature through that, we're still going to generate a voltage. Okay, but we would lose any kind of basically fine tuning or altering of the field if these are permanent magnets. Okay, there are lines of force going through here, but we can't change them. We can't make them stronger or weaker. So whatever output we get in this scenario, that's the output we're going to get. This is the scenario where we have current flowing through these windings through onto the other side, and which creates a north and a south pole, so that when this armature spins through here now, again, we do have magnetic lines of flux through here, but we can adjust the intensity of these magnetic lines by how much current we have going through these field windings. Okay, so you'd have a rheostat in series with this, basically controlling how much current goes through there. Okay, so it's just something I usually draw out just to kind of help. I got caught up on that a bit for some reason. I don't know why it kind of killed me, but it did, so I try to make a point. This is just this is apparently not good to see because of my pencil. I'll see if maybe if I zoom in, if it gets better. A little bit here. Okay, so these are just some kind of notes that I've made myself about the field winding, where it's located in DC, what it does. So the field winding, it creates magnetic flux, and it is electromagnet. In DC, the field winding is on the stator, so that's the stationary part of the machine. The armature is on the rotor, that's the rotating part. That's where voltage develops. Voltage always develops in the armature, whether it's on the stator or the rotor, okay? So if we just come look over at the AC, our field winding, in this case, is on the rotor, okay? And this is in your definitions in that module. But what does the field winding do? It still creates magnetic flux. It's still an electromagnet, so its job is the same. It's just located on a different position, or a different portion, sorry, of the machine. And we'll talk about why that is in AC when we get to it, why we don't want the armature spinning, because we have large currents going through there, and we'd have to have huge wires on our rotor, which we don't want. Okay, but in AC, our armature winding, so that's where, again, where voltage develops, same as it is over here, but it's on the stator. Okay, our output, so for DC, we have split rings commutation, and our output is a DC ripple, okay, a pulsating DC. In AC, we have slip rings, and our output is a sine wave, okay? Other things we want to make sure we know, our Fleming left-hand rule for generators. Again, our thumb is the motion of the conductor. Our index finger points the direction of the field from north to south, and then our middle finger is going to show us the current flow. In DC, if we want to improve the wave output, we increase the number of armature coils and commutating bars, obviously, because then we have multiple windings, so we need to have multiple contact places on our brushes. This decreases the magnitude of the ripple. Again, it smooths that out and increases the average value of voltage because we don't get down to those zeros. We're staying up high on those pulsating ripples. So we don't get these big drops. We stay up here and we get a higher value because of that. And again, how are we going to control that output voltage? Changing the field current. That's how we're going to alter the output. Okay, the magnitude of voltage that we're going to see out is going to be done through that field rheostat on our field winding. Okay, so that's usually stuff I put on the board while I was lecturing too, just to talk about this. So hopefully that kind of gets you into the generation stuff. I'll post this here, and then again, we'll review some of these concepts in lab. But yeah, use that for what it is. Hopefully it helps.